And now from in space to outer space, I'd like to introduce our speaker, a gentleman from the Jet Propulsion Laboratory up in Pasadena, who was kind enough to drive down here this morning to speak to us. Steve Matousek, who's sitting over there in the blue shirt. Steve, thank you very much for coming down. We have great anticipation of what you have to say this morning. So a little bit of background about Steve. He's been exploring Earth and the solar system and the universe via robotic probes for over 30 years. He began his career in aerospace as a student command controller of the Solar Mesosphere Explorer at the University of Colorado in Boulder, Laboratory of Atmospheric and Space Physics. He's had the honor to have worked on the Voyager, the Mars mission. He was one time the manager of the Juno program, which is on its way to Jupiter. 5 years of flight, correct, to get there? When will it arrive? 2016?
July 4th, 2016.
2016. And many fascinating advanced concepts for the future. He's an aerospace engineer and obviously a man who likes heights because he enjoys mountain biking, he tells me. So come on up, Steve, and let's hear what you have to say.
Steve, keep your microphone.
It fell off. It's not good. I turned it on. Okay, is that working okay? People hear me fine? Okay. I didn't go to sleep, but my computer went to sleep. So let's see. So, thank you for coming today. I'm very honored to be here to talk about space exploration. I was inspired to work in exploring the solar system and other solar systems when I was 6. I watched Apollo astronauts walking on the moon, and I said, wow, I got to do something like that. So I decided I went to University of Colorado, got the chance to command a satellite when I was 19, and I came out to JPL, and I said I'd stay there as long as I was having fun, and I've been there ever since. So what I want to do today is we'll take a whirlwind tour of our solar system. We're going to stop a while at Jupiter, and then we're actually going to talk and take a quick tour of some other solar systems about exoplanets. We live in a very, I think it's a very unique time right now where you see in the headlines almost every week there's some new planets discovered in another solar system, and we're starting to compare our solar system to other solar systems, and it's an amazing time. So I hope to give you a flavor of that this morning. Now, let's see here. If I hit the right button.
Sorry.
No, it's okay. I think I got to start first. I have to turn it on. Talking about space probes like you. There we go. Okay, so let's start out. Of course, back over 400 years ago, Galileo discovered. Sorry, I'm standing in the way of the slide. Built the first telescope and took a look at Jupiter, and this is a sketch in his notebook of what he saw. He saw Jupiter and then 4 dots that moved around. So he discovered, of course, the Galilean Satellites. And that led people to think, well, you know, if satellites can circle around another planet, well, you know, our solar system, the planets circle around the sun, and that was pretty revolutionary at the time. This also is a picture that many of you probably look through telescopes, and you can see Jupiter almost any time, and the Galilean Satellites. It's really, really interesting to look at. I love to look at them and then look at it a couple hours later, and they've moved around. So I'm going to concentrate this morning on the outer solar system. Of course, we have, and this is to scale, but not to distance. We have the sun, which is the largest thing in the solar system, closest star. Then we have these small rocky planets in the inner part, and of course the Earth is here. And this is to scale, so Jupiter is here, Saturn, Uranus, and Neptune. I'm not going to talk about Saturn, Uranus, and Neptune very much today. I'll have to come out again and talk about those. So let's zoom in a little bit on the outer gaseous giants. They're made up of mostly hydrogen and helium. There's some other gases in there like methane and things like that, and it varies between the outer planets, and that's why they look different colors. They also have different, like Jupiter has banding on it, Saturn has a little, it has a huge ring system. Then Uranus and Neptune over here, they're kind of bluish, and they have more methane in there, and they're smaller. About 11 Earths fit across the diameter of Jupiter. So when I talk about Jupiter later on, it boggles my mind actually. I mean, Jupiter's gigantic. And even the Great Red Spot here, which is a storm that's been raging on Jupiter since Galileo looked at it through his telescope, over 400 years, is the size of the Earth roughly. So it's pretty amazing. There's other storms that are on there. These bands going back and forth, the winds, the differences between the airspeed between the bands is about 1,000 miles an hour. So it's quite chaotic there. One of the big questions about our solar system, and actually for other solar systems too, is how did Jupiter form? If we understand how Jupiter formed, we understand how the Earth formed. Because remember, we had the rocky planets on the inner part of the solar system, and Jupiter's really good at, if comets and asteroids and other bodies that are smaller come close to it, it either flings them out of the solar system or flings them into the sun with gravity assists. And so how was the Earth and Mars and the other rocky planets able to form in the inner part of the solar system? It's still a big mystery. So one way to start unraveling that mystery is find out what Jupiter's made out of, what the core is made out of, how much water is there. Is there a solid core? We don't even know some things like that. On the Earth, we know more about the core and things like that because we're right here on the Earth. At Jupiter, we don't know that. We don't know how far down these different bands and clouds and stuff, how far down does that go? There's also a region here which has some pretty weird stuff, I would say. It's at a pressure and temperature that if you take hydrogen and you squeeze it, and of course the temperature goes up, it can become metallic hydrogen, meaning all the electrons free up and they move freely in there. Now hang on to that thought for a second, because we'll talk about something else at Jupiter that's really, really cool. So if you have metallic hydrogen in there, we can't really simulate that here on Earth. They've done some experiments where they take explosions and they take a little bit of hydrogen and they'll squeeze it to try and simulate these conditions, but they can't quite get there yet. So, now I wonder how do I play that? I have a couple movies here to show you to illustrate how the bands move and some other things on Jupiter. I think I have to do it this way. So, on the left, here, you see Jupiter, and I'm going to play a short movie that'll, there it is. Oops. Oh, there. Okay, cool. I just click on it. So you can see that this is if you're rotating around with Jupiter. Jupiter rotates around once every 10 hours, so a day on Jupiter is 10 hours long. That's because when it first was condensing from the gas and dust in the early part of the solar system, it's still got that rotation left over, just like you see ice skaters when they're going close. Jupiter also gives off more energy than it gets from the sun. So as it collapsed, all that energy is still there and it's coming out and it's powering all these different storms and the banding. The other movie is a little bit different viewpoint here. So before I play this, let me orient you here. So you're looking at the south pole of Jupiter. Now, you probably go, how can I have a movie of the south pole of Jupiter? Because we haven't sent a spacecraft there yet. Well, we have had flybys of Jupiter, and they get just enough of an angle so they can barely see down to the pole. They can't see quite down to the pole because there's a little spot here they can't really. So they put all these frames together in the computer and they make a movie. And the reason I wanted to show this is because you'll see it rotating around, but look at it. I'll play it twice actually, because sometimes you'll see things moving and sometimes you won't. So you're looking at the south pole of Jupiter. As you go towards the outside, it's up to about 60 degrees south latitude. Right in the center is right at the pole. Let me play it one more time. So you're rotating with Jupiter. Some things rotate fast and other things don't. Like in the very center, they don't know why this happens, and so that's one of the reasons we want to go back there. Some of these things are actually moving backwards compared to other things. So it's quite strange when you have a big ball of gas and liquid and it's rotating every 10 hours. Remember when I talked about metallic hydrogen and how all the electrons and stuff were moving around? Well, that's probably what drives the biggest magnetic field in the solar system besides the sun. Jupiter has a huge magnetic field and it's very strong. If you were able to be somewhere around here near the top cloud tops, it's not solid. It's gas. So, but if you could somehow be there, the magnetic field that you get is 10 times what we get here on Earth. So it's very powerful. That drives electrons and protons that go around on these magnetic field lines. Have you ever seen take a bar magnet and you put little iron fillings on there and you can see the field lines? Well, that's what this artist concept shows here. And also in the center parts of this here is intense radiation. Electrons and protons come around and they will interact with anything you send in there. So hang on to that thought, and when we talk about Juno, I'll talk about how we protect against that. Because if you fly electronics through that radiation, electronics don't like that kind of stuff. It zaps them and they'll start arcing and not work. I put in another movie here to show, so this is going to be rotating once every 10 hours with Jupiter, but it shows how the field lines move around to try and give you a better idea of that. Okay, so see these, oops, sorry. This is the North Pole and it's rotating and the field lines move around. Now we're looking down on it on the North Pole. So imagine the solar wind is coming in like this and it's moving the field lines around all the time. This happens on Earth too, when you hear of a magnetic storm coming from the sun, but these are 10 to 100 times bigger than what we get on the Earth. So what you're looking at here is one of the only pictures we have of the North Pole and what the Aurora looked like. So on the Earth, many of you have probably had the chance to see the Aurora Borealis when you get to the northern latitude. Sometimes even down here in the U.S., not often, you'll see the Aurora Borealis, which is caused by particles from the sun hitting our magnetic field, interacting with the atmosphere, and it gives off light. Well, this is happening at Jupiter too, in the pole. This is from a Hubble Space Telescope picture. And the thing about this, though, is across here you fit about 5 Earths. So it's gigantic. The huge magnetic field is sending particles in, and it's zapping the particles in the upper atmosphere. Now, another thing here, you see the labels here. It's got Io, Ganymede, and Europa. Well, those are satellites, moons that are moving around Galilean moons, and so as they move in their orbit, they intersect those magnetic field lines and they create a pattern that you can see as they move around, which to me is just, wow, that's amazing. How can you see satellite traces in the Aurora on Jupiter? We don't know why that is, but when we send Juno there, we're probably going to have a lot more information about why that is. That also happens at the south pole of Jupiter too. We just don't have pictures of it. So Why do we want to send another mission to Jupiter? Because we've sent others. We had Galileo there before. Galileo, we even sent a probe into Jupiter. Don't we know everything?
No.
Excellent. Talk to me after that. Galileo sent a probe in there thinking that we wanted to know where the water is. Now, why is it a big deal about water? Well, when the solar system formed, the temperature and conditions where a planet formed or other things, asteroids, comets, and allowed water to be there or not. In the outer part of the solar system, there was more water, in the inner part, less because of the heat. So one big mystery is, where did Jupiter form? Did it form far out, or did it form close in? And so if we know how much water is there, we compare it to the sun and other places. So they said, okay, we're going to send a probe in. It's going to go down through the atmosphere. It'll, before it gets crushed by the pressure and temperature, it should pass through water clouds and ammonia clouds, and we'll find out how far they are down, and we can figure out from models how much water is there. So that sounds all great, but you send this particular probe went in, it goes down through the atmosphere, and it never went through a water or ammonia cloud. There was no signal that came back before it got crushed. And it got crushed at about 14 times the pressure here at the that we're experiencing here on the surface. So, and they thought, well, what does that mean? Some people say that it was like a desert, that we went into a special place on Jupiter and it didn't really, that particular part didn't have any water clouds. And others say, well, the water clouds are down deeper. So that's a big mystery right now. We don't actually know how much water is at Jupiter. Also, we'll hold that thought when we start to talk about Juno and why or why not we'd send probes. So all of this leads up to the Juno mission. Juno is actually out in space right now, and it's getting ready for an Earth flyby October 9th. I'll explain why we're going to fly by the Earth again and get out to Jupiter. That sounds a little crazy, but it works. So Juno is headed out now, and in order to investigate Jupiter, you need to look in different wavelengths, not just visible light. So some examples of that are, we look in ultraviolet light, infrared light, because you can see down further or see different phenomena. We're even looking in X-rays and other things like that at Jupiter. So when Galileo saw visible light, now we're extending what we can see by putting different sensors and instruments on the spacecraft. So Juno, just the overview of the mission is, it's a big spinning spacecraft, and it's the first solar-powered spacecraft to go to Jupiter. The reason that we made it solar-powered was that it's actually cheaper and more efficient to have solar power out of Jupiter than radioisotope power. Most of our outer space, deep space probes are radioisotope power, which is plutonium oxide decay. But it was cheaper because over the last couple decades, the solar cell industry has really driven better efficiency and things like that. So now we can extend out how far in space we can send solar cells. It takes 5 years, as Patrick mentioned, to get out there. I'll explain more about that. And then it's at Jupiter 1 year, and I'll explain in a little bit why 1 year too. It has to do with the radiation that I was talking about. So the spacecraft itself, if you could stand it, this isn't actually me, but it's about somebody my height there, the outline. And you'd be about halfway up on the spacecraft. So it's quite tall. It's about 15 feet tall. And this is the antenna that sends back the radio signals. The total diameter around here is 20 meters, or 66 feet. Usually I talk in metric units. And I actually think in English units, so that's kind of interesting. Here's the big solar arrays. They have 4 segments each, and they have a total of over 40 square meters of solar array. Now this is not unusual though for geosynchronous communication satellites. They actually have about that much solar array, a little bit more. Only they're at Earth, so they get more power out of it. The solar arrays give us about 440 watts when we're at Jupiter. You also notice that not all the solar arrays are the same. And you probably would ask me, well, why is that? Well, this particular one here is unique because it contains the magnetometer instrument. The magnetometer wants to sense the magnetic field of Jupiter so we can model that and figure out what's in the interior of Jupiter. But we put it way out here with with minimal wiring and things like that because we don't want to sense the magnetic field of the spacecraft. Instead, that would be a bummer if we went out to Jupiter and we were sensing the magnetic field of the spacecraft. Because it has electronics and things, and as electrons move around, of course, it creates a magnetic field. So it's way out here in the end. This boom is specially made to be very precise and not flex and also not have its own magnetic fields. There's other sensors that are all the way around the spacecraft too, and they're all spaced out there. They have fields and particles. So as Juno spins, it's sensing a whole bunch of the different fields and particles out at Jupiter to model and figure out what's going on out there. There's also a visible camera. We put it on not for science, but said when we're flying over the pole of Jupiter, if you don't take a picture, so we put on a special camera. The camera though is not like you have with your cameras. It has it's like a fisheye camera. It has a 53-degree field of view because as we fly over the pole, we're pretty close, and so it's sized to fill up the frame. That's the picture I think in 2016. That's the one that'll end up on AppWeek, I think, is when we fly over the pole, it'll take that picture. That'll be very cool. It has ultraviolet and infrared, and those are, the infrared one is donated from the Italian Space Agency. On the bottom part, there's a whole bunch of stuff too. There's a main engine here. We needed, in order to get to Jupiter, we have to do some big burns with the propulsion system. It has a cover that can cover it up, because on the way out to Jupiter, there's actually there's dust. We're not worried about the asteroids or comets or anything like that as we go out to Jupiter. What we're worried about was little pieces of dust. Because as the spacecraft goes out there, these pieces of dust can hit, many, many times the speed of a speeding bullet. And so down inside this engine is a special coating, so it keeps it from burning up, basically. If a piece of dust were to hit that at the wrong angle, then we'd do a burn and the engine would burn up. So there's a cover that we open up every time before we're going to do a burn. There's antennas here to measure radio waves, and they're all, other thing here too is it gets very cold out at Jupiter, so there's thermal blankets to keep everything warm. That was a big deal out at Jupiter because when it gets cold, how do you keep it warm when you just have solar power? You need to use that power. So down inside there's a lot of attention paid to keep things from freezing, like the propellant and things like that, and keeping the computer at the right temperature. Electronics and computer components and stuff, they like to function at room temperature, and so we designed it that way so we could use readily available components that don't cost a lot of money to be cost effective. I just threw in a few facts here about Juno. It's coming towards the Earth again. I think one of the interesting facts down here is that of the fuel, it's burned about half of it. Juno, when it launched, was about 2/3 propellant and 1/3 structure and other things, and so it was just basically a big gas tank, and we burned about half of it. I'll explain more about that in a bit here. One other thing, when Juno gets to Jupiter and it's at its closest approach point, close to Jupiter, it will be the fastest human-made object that we've had in the solar system. And the reason for that is Jupiter is gigantic, so as we get close to it, Jupiter accelerates Juno and it'll be going 58 kilometers a second. Now, to sense what's in the core of Jupiter though, with radio Doppler shift, we measured to about 1 millimeter per second out of that 58 kilometers per second to figure out what's in the core and where mass concentrations are. I put this in because it's a major partnership to put together a space mission. So there's places all over the country. Down in San Diego, there's a visible camera at Space Science Systems. Lockheed Martin Denver put together the spacecraft and integrated everything. Of course, they also have a launch vehicle. Southwest Research had a couple instruments. It launched from Kennedy Space Center, Goddard Space Flight Center, and Johns Hopkins University Applied Physics Lab. They have an instrument. We also have international partners, which it takes for this size mission, it usually takes international cooperation. So we had the contributed infrared instrument from the Italians. The Danish Technical University has some star trackers. Basically, that will look at the star field, and as you rotate, it can tell you where you're at in space very precisely. And the Belgians provided also a sensor for the ultraviolet instrument. I couldn't help putting in a picture of the launch vehicle. It launched August 5th, 2011 from Kennedy. This was from the night before. Now, I mentioned, why do we go in a loop instead of just going out to Jupiter? If we designed the mission to go straight to Jupiter, it would have taken a Delta IV Heavy, which costs a couple $100 million more than we had in our budget, because this was a competed mission for NASA, and they said, well, the cost cap is $1 billion. You can't go over that. So we couldn't afford to buy that, so we designed the trajectory. It launched, and then it goes on a 2-year loop. It does a major propulsive burn out here. It did that last year. And then that lines it up for an Earth flyby on October 9th. And when it does the Earth flyby, that of course gives it energy with the gravity assist enough to go out in a little less than 3 years out to Jupiter. So that saved a couple $100 million to do that. Plus it allowed the spacecraft, they got to kick the tires and see how it was performing for the extra 2 years, which is a big benefit too. So at Jupiter, I mentioned that we're going over the poles, but what does that mean? So imagine now, you're looking at the equator of Jupiter, at the plane of all the Galilean satellites orbit around in the same plane around the equator. So this is the orbit that's going in over the poles, over the North and South Pole. I'll show you a better close-up. Now, on July 4th, 2016, it was not designed on purpose that way. I swear, it just came out that way at 8:30 p.m. local time here. We'll do a burn to put it in an orbit. Now, the first orbit it goes into is 107 days long. It's not the final orbit. We have to do another burn after 107 days to put it into an 11-day orbit. That turned out to be more efficient. If you break it up into 2 burns like that, it saved a couple 100 kilograms of propellant, which translates into money and efficiency. So after it goes into these orbits, here 11-day orbits, it does 33 of those. It takes science on 30 orbits, and at the end of that, we'll do a burn and go into Jupiter. I'll talk about that a little bit more. Why does that orbit move like that? So I took a snapshot here, the first orbit, 16th, and the 31st orbit. So Jupiter's gravity torques the orbit around like this. So if we continue the mission, it would just continue to torque around and take about 12 years to totally rotate around. Now the problem is, early on here, you see the red and yellow is the radiation zones. So early on, we're not getting much radiation. Later on, we start to get more, and then at the end of the mission, we're going through a lot of this red and yellow. So in the first half of the mission, we get only 20% of the radiation, and then we get 80% in the second half. And that's why we want to end the mission. We say, okay, as we get out here, it's taking a radiation hit every time it goes close to Jupiter to take the science measurements, and it's just too risky after that. Every orbit, just a bigger and bigger radiation hit. We said, well, at that point, we're just going to do a maneuver to go into Jupiter. We don't want to leave it uncontrolled in Jupiter orbit. So how much radiation does it get? Certain parts of it get a lot. In the inner part here, there's a vault that was specially designed. It's another first for a deep space mission. The vault is made of titanium, and it's a honeycomb that's about an inch or so thick. Titanium is very efficient it's fairly easy to machine. It's also very efficient at stopping these particles that are zipping around. And so we could put regular commercial space parts inside the vault, and those are protected. But outside, what do you do outside the vault? The We have to use special designs for some of the sensors, things like that. Now, it turns out solar cells, the radiation doesn't really hurt them. It does a little bit. Like, we lose about 10% in the efficiency, but we can just put a little bit more solar array on. So that's very fortunate. The thing that gets the most radiation is, of course, the cover glass that's on top of the solar cells. Now, this all had to get tested before launch, so there's only a few labs on Earth where you can zap it with radiation and see what happens. And so they put the cover glass in there to make sure it wouldn't darken and all those kind of things. Now, why do we take science for 30 orbits? Why is 30 a magic number? Well, if you have the scientists who do the magnetic field modeling, they said, well, we'd like to have a closest approach here where we take measurements, say, every 10 or 12 degrees. So every 12 degrees, 360 degrees, that's 30 orbits. So they have to be controlled very precisely in the outer part. Go back here. In the outer part of the orbit, every orbit, we do a small maneuver out here to make sure the timing stays right. So it lays down these very precise tracks. In the first half of the mission, it does those at 24 degrees, and then we do a little shift, and it fills in the gaps for the second half of the mission. Now, I'm going to pause on Juno for a second, and I'll stay here. As long as people want to ask questions afterwards, I'll stay to answer everything, because I know I'm going pretty quick through stuff here. Now I wanted to pause, though, and say, okay, we know things about our solar system, and I mentioned about exoplanet, extrasolar planets in other solar systems. Well, how do they compare? Why do we want to know about exoplanets when we have all these planets that are close in our solar system? Well, one of the things that if you read the headlines and find out about the exoplanets, most of them that we're discovering are like Jupiter or bigger. Now they're starting to get down to be able to discover some that are the size of Uranus and Neptune. They call them icy giants or icy planets. But we haven't found anything like the Earth or the other rocky satellites yet. But I think we will, but we just haven't done that yet. So where are we with exoplanets? Now, last year we discovered almost 800. Now I think I looked at the log of how many they have, and they're over 900 now. So they're discovering them a couple every week at least. This is a depiction that somebody on the web had of the sizes and temperatures of them. And as I said, these bigger reddish brownish ones are like Jupiter, so they're easier to discover. So that's how we know most of them are out there. How do you discover these exoplanets? Because they're so far away. I mean, they're hundreds to thousands of light years away. So there are three main techniques. The one that's mostly been used is the transit method. So if you everybody take your fist, and you're going to be the star that we're sensing. So take your fist, and the transit method. I don't see many fists. Okay, well, so if you're observing and if you're the star and you have the planet moving around there, as you look at me, it's going to go in front of, it's going to make a transit. So the star will blink on and off. Some of the starlight will be lost, and you'll be sensing some of the light that's coming from the planet. That's the basic technique of how they discover a planet. They'll see a dip in the amount of light that's coming from that, and they very precisely can measure the characteristics of that light. Now, this is a great method. One of the issues with this is it means that you have to have the planet lined up in the right place. If the planet's orbiting around like this, there's no transit to look at. There's only about 10 to 15% of the other solar systems that we're looking at that have transits, that are in the right geometry. So if you can't use that method, what else can you do? You can directly image the planet. Now, to me, that sounds kind of mind-boggling, because there's a star there that's really bright. I mean, you're actually going to see a planet that's thousands of times dimmer. Well, the Hubble Space Telescope was able to do it a couple of times. This is you probably saw this in the headlines back in 2006. What they did was they took a picture of Fomalhaut, the star, and they thought, okay, we want to try and see if there's any planets there. And so they took a picture in 2004 and in 2006. Then they compared the pictures and they see what's moved in all of the stuff that they see. Now most of this here is really just the computer processing they have to do on it, because they have to make it really, they're doing very precise, and they have to magnify it and make things more visible. So a lot of this stuff is really, if you compare the two things like they did here was this planet in 2004, here it was in 2006. So they directly image an exoplanet. That's only been done a couple of times. I think this will be used more as telescopes get bigger to look directly at exoplanets. So that one, the planet could be anywhere around the star. But you really have to make sure it's a planet, because there's a lot of other stuff out there it could be. So once you've found an exoplanet, how do you know anything about it? We know orbit, things like that. If you take the orbit as it's going around and the different transits as it's going in and out, and you put a spectrometer on that, spectrometer just splits the light up and looks at how it gets absorbed in different places, and then compares that versus modeling. You say, okay, if there's methane in there and water in there, it would look like this or not look like this. And so in the computer, they're doing many fits to it, and then you can tell if it has methane or water in the atmosphere. This has been done about 8 to 10 times now, where we found water and methane in other large exoplanets that are bigger than Jupiter. That doesn't mean that it's rare out there. It just means that it's very hard to do right now. And you need to be very precise when you're pointing and have thermal stability. I put a few figures in about that here. These are artists' views of what some of these exoplanets look like. So they're not actual pictures of them. But I think, within 10, 20 years, we'll start getting some actual pictures. This particular planet is typical of the ones that get discovered. This is bigger than Jupiter, and it's very close to the star, so it heats it up really hot. And we, before we started discovering these, we said, well, that couldn't happen because it'd be too close to the star. How can that exist? But it's there. Other types of planets are around, if you've heard of red dwarf stars, like the star is over here, but the planet is rocky. It's just too close to the star, so it's going to be made of lava. It's too hot. There's another star, this particular system has 2 planets in it, and one of them's bigger than Jupiter and really hot, even closer. So these are to me, they're very strange. We don't have anything like that in our solar system, so we're finding these other examples of other solar systems that can exist. Now, another thing I wanted to talk about was, when you hear in the headlines it says, we found a super Earth. Well, what does that mean? Super Earth just means that it's a few times bigger than the Earth. So this is to scale. This is the Earth, and this is a super Earth. And the super Earth, all the ones we've discovered so far are really close to the other stars, so they're hot. Even though this is blue, don't let that fool you. This one's probably about 2,000 degrees. It has water vapor in it, but it's big, so it's not really couldn't support life there. But that's generally what's meant by a super Earth. Now, you've also heard about the habitable zone, probably, which means you go to another star. Well, let's take this is our solar system, and this is another solar system discovered by Kepler. So our solar system has a certain range here from it that liquid water could exist on a planet. Now, that doesn't mean it does, because of course we have Venus here that's way too hot in our solar system. But if it was like Earth, it could have liquid water. So habitable zone just means liquid water on the surface. Now Mars, we know, does have some water on it. It's mostly ice, but it does have liquid water. Of course, Earth is made up of 70% liquid water. So if you take that to another solar system, you say, okay, here's the star. Here's the range where liquid water could exist. One of the planets here, super Earth, is too close, so it's too hot. Even though it's blue, again, don't let that fool you. It's really hot. Another of the planets is kind of on the outer edge of the habitable zone. So if it's even much bigger than the Earth, but if it had the right conditions there, it could have liquid water on it. So that's what's meant by the habitable zone. We haven't found many planets in other solar systems that could exist in the habitable zone, but we're starting to be able to see those more and more. So what kinds of instruments discover this sort of thing? Of course, there's Hubble, which was never meant to do that, but it's such a great telescope that it's able to look at other planets. There's CERTIF, which is another type that looks in the infrared. There's future missions. This was one that was proposed last year that would be dedicated to looking at 200 exoplanets over 2 years. And then even ground-based telescopes are starting to see these sort of things. So it's a really interesting field right now. A lot of students are going into this. Exoplanets are really cool to look at. I'm starting to run out of time, so I'll just say that out in space you need a fairly good telescope and a good detector to do that. I can talk about that if people want to ask me about it. Now, I also go to schools and we talk about exoplanets, and I go through an exercise where they get to draw their own exoplanet. We talk about the different kinds and stuff. This is an example of one of the exoplanets that one of the students drew. And this one actually even had a moon around it. I said, wow, these exoplanets would have moons too. So I think that's really cool that kids love to imagine what the exoplanets are going to look like. They draw it much better than I could. It's really interesting. So one of the NASA artists redrew our view of what just a small slice of the universe and put that, there are planets around almost all the stars we know. We thought there were hardly any, and now as they discovered more and more, we think that 50% or more of the stars have planets around it. So I think I ran out of wind here. I'll stay here to answer questions. We can take some from the audience now. Thank you very much for the Yes, sir.
Our solar system is supposed to be 16 billion years old, and not our solar system, the universe, and 4 billion years old for the Earth. Do they ever figure out where the Big Bang came from? And with 16 billion to 4 billion, a lot of this other stuff in between has been burned out.
Okay, so let me try and I'll distill that question. So the Earth 4 billion years old, the universe 16. Sorry, I'm paraphrasing. What's in between and why those numbers? I can't give you a full answer.
Where was the Big Bang?
Where was the Big Bang?
Yeah. Do we know where the Big Bang happened?
No, I don't think we do. We keep seeing further. Well, we keep seeing further and further back in time as telescopes get more and more powerful. They can see back to within a billion years probably of the Big Bang. And then this is way out of my field, so I don't. The Big Bang part of it. Now, let me talk about the 4 billion for Earth though. They think that our solar system is a second generation. So another set of stars went supernova, and when they go supernova, they of course it's a big they blow up. There's a big explosion, and it puts out a lot of the elements that we have in our solar system because they couldn't have been made any other way. And then our solar system condensed from that gas and dust over second generation, or maybe third. I can't answer the rest of it very well either because it's a big unknown right now. Let's see, there was another question here. Yes.
Is everything actually in a circle, or is that just is that because they're spinning, or are these things not?
Oh, are the planets their orbits circles? No, they're not. They're not all circles, and that's in fact they're all slightly elliptical one way or another. Some of them look like they're a little bit like in our solar system. Pluto is very elliptical, and some of the other planets that they're discovering are. Now the ones that are really close, I forgot to mention that a lot of the orbits, like they have these gigantic, bigger than Jupiter-sized planets, their orbits around their stars are like 4 days. So a year on that planet is 4 days. And so when they get that close, they are circular because they're so close to the star. Now when they're further out, they are more elliptical.
In those exoplanets, are there stars about the same size as our sun?
Yes.
Or bigger?
They're mostly our sun size. Some of them are the red dwarfs that are smaller. The big stars that are much bigger than the sun, we haven't really seen exoplanets there yet just because it's hard to get the right conditions. I think, this is me just speculating, I think they're there. It's just the techniques used that I was talking about, when the star is really bright, it shines so bright you can't see other stuff there yet.
Isn't the habitable range a function of how big the star is itself?
Yes, it is, right. The smaller stars, the habitable range is closer in, and for the brighter stars, it's further out, yes.
Do you have any expectations for what the inside of Jupiter might end up being? Or if there will be like a solid and a liquid core? Or
Can you repeat that, please?
Yes, the question is, do I have any expectations about what would be in the center of Jupiter? Is there a solid core? What's there? Let's go back to one of the pictures of it. I think, if I were going to guess, which I will now, I think there's probably a very small solid core that's probably about the size of the Earth, maybe a little bit smaller, and then there's a big region around it that's metallic hydrogen, because I can't figure out any other way, and the scientists can't either, about how you can make these huge magnetic fields. You've got to have a lot of electrons moving around inside there, and the only thing that could be there with that many electrons is something like metallic hydrogen, which, if that's there, we'll be able to detect it with Juno and figure out how big it is and how it's moving. Another interesting thing I didn't mention, but the magnetic field is not centered on the center of Jupiter. It's offset by about 1/10 the radius of Jupiter. So how's that happening? You know, when you have metallic hydrogen moving around and stuff, we don't know. And then out from there, I think the cloud tops will extend quite a ways down, and maybe a little bit further than we think. That's just my guess. I don't know, back in the blue shirt, and then I'll.
Two questions, please. I saw a civic recently that they discovered a few more moons around Jupiter.
Yes, I forgot to mention. I mean, they're discovering moons all the time. Some moons. What's the count now? I don't know. It's like.
I think they mentioned 60 something at JPL yesterday.
68, something like that. Jupiter and Saturn are in this contest for moons. You know, you discover some Jupiter and they just keep going up. But it's high 60s now, I think.
Second part, do all moons generally orbit at the equator of all planets?
Generally, yes. They almost.
That don't.
I believe Pluto's moon, Charon, probably orbits not at the equator, but that's a smaller side. I mean, that's a dwarf planet. I still say planet. It's a dwarf, and it's smaller, and it has another, and it's not orbiting exactly in the equator. But all the ones in close, like Saturn are closer, they're all in the equator. Let's see, there was this one, and then I'll get to some others.
Well, I was just curious about the qualifications for a super Earth. Is it all predicated on the periodic table elements? And how does that?
It's just size. Right now, it just says if it's. They don't really have since it's such a new field, they don't say, okay, it's got to be 1 point something. But if it's generally Earth size up to 5-6 times the size of the Earth, they call it a super Earth. If it's bigger than that, they start saying, oh, it's 0.5 Jupiters or things like that. Yes, sir.
So what the heck is metallic hydrogen? How did you discover hydrogen as a gas or water? Where do you get metallic hydrogen?
When you put a pressure on it of 1 million to 2 million atmospheres, it compresses it so much that it can become, the electrons are stripped off, just like in metals. Metals have free electrons, and so when hydrogen is actually in that column in the periodic table, if you did that, it strips off the electrons and they can move freely. And so if it's at that pressure, it goes into that state. One second.
That was part of my question. He just asked part of, metallurgically speaking, when you compress hydrogen to that density, does it form a particular lattice structure, such as say a face-centered?
Oh, I don't. They haven't been able to create it.
Okay.
So
They can't duplicate that lattice.
not yet. No, they're getting close in some of the Earth-bound experiments in labs and stuff. But it's actually a very tricky thing to compress something that much. And so they take diamonds, precisely ground, and they put hydrogen in between it, and I don't know that much more than that about it, but they're getting close to recreating those conditions, but they're not there yet.
Should we imagine metallic hydrogen as being like a solid or like a gas, or how, what does it act like that way?
I don't know. I don't think it would be like a gas because it's so compressed. It would be, things are so close together, it would be kind of a liquidy solid, or solid liquidy.
Glass. Like glass.
Like a glass. Okay, one more question. Yes, sir.
I understand that the solar system is expanding faster all the time and it's not slowing down. Is that true? And if that is true, is it because of your hypothesis that the Big Bang is forcing, or is there something out there pulling it to make it increase?
I'll make the answer short, and then we can talk later. The universe is expanding faster all the time, which to me is somewhat troubling. But I'm like, what do you mean? So, but what's causing that? They don't know. If you go to dark energy and dark matter, they're trying to figure out now why is the universe expanding faster than accelerating over time, and they don't know. That's why you see all these different theories and stuff about what's happening. It's a very interesting one. Thank you.